Hello, Ayoub.
Hi there.
How are you doing today?
Yeah, I'm good.
All right, all right. Where are you joining from today? Are you in Colorado?
Yeah, I'm in Boulder.
Ah, nice, nice.
Yeah.
How do you feel about the Adapt FM challenge?
Mm, it was good because it's the first time playing with the LLM serving stack. So I had
Yeah,
to, yeah, I had to patch SGLang a lot. It was fun.
yeah. The so the other guy that was really working on it is
Yeah.
sitting in here. He just walked out, but yeah, we were like racking our brains trying to figure out how to actually get it to even pass.
Yeah.
We spent weeks, I think, couldn't figure it out.
Yeah. Yeah. The logistics part was definitely lacking. So like it was not pretty clear how to deploy stuff, but you know.
And here was Abhishek. So this guy actually found out a lot of like tricks early on.
Well, I mean, there was one thing we could never figure out, but yeah.
Yeah.
Yeah. Yeah, we're debugging things until like 2 a.m. or something.
We have like an agent flow that's designed to run like verification on it and basically explore and like find maybe like why it's not fail or why it's not working.
Yeah.
And we tried to like run it on this and it worked. Like we actually did get something close to what the top score got, but then every time we like deploy it, it would always just break somehow. We could never get the logs.
Yeah. I guess starting early was definitely advantage.
Yeah.
Yeah.
It just shows you can't always rely on AI for everything.
Okay. I guess there's more people than expected, but anyway.
Yeah,
Okay.
usually until like I want to say 34, 35. But if we have a good credit level, we can start sooner.
Yeah, just give me the signal and I'll go ahead.
I'll do.
You want to make sure you can share your screen while we wait another minute?
Okay.
Good call.
Mm,
74. No way. He's going.
So this chat
Is that?
yeah. You find it cold or hot? Cold?
Let's see there.
okay. Yeah, I was hoping I would get to quantization, but I think I have enough material for like just the sparsity pruning for now.
Yeah, I would like to I think ask questions and have discussions as well. So I think if it comes up or you want to talk about it, feel free to like show whatever you want.
Okay.
So we want to start now or no? Okay, yeah. I think yeah, I think we can go ahead and get started. All right. Should we start recording?
I think.
It's already fun.
Oh, I see. There you go. That's okay. All right. Well, welcome everyone to today's random sample seminar. It's my great pleasure to introduce our speaker, Ayoub Ghriss. So Ayoub actually recently defended his PhD at the computer science in computer science at the University of Colorado Boulder. So there he was advised by Professor Claire Monteleone in the Climb Lab. And before his doctoral studies, he actually earned his engineering degree in applied and computational mathematics from ISO Polytechnique. And then he actually got a research master's from ENS Paris Saclay. So his research operates at the cutting edge of machine learning, focusing on theory and GPU-accelerated algorithms for structured sparse training, differentiable graph partitioning, and efficient neural emulation of climate dynamics. He also brought this expertise to industry through research internships at Google, working on satellite imagery for air quality, Amazon Alexa, working on speech and paralinguistics, and at Riken AIP, researching deep reinforcement learning. His work has been highly recognized by his peers. He actually earned the Colorado University Boulder Computer Science Department's Outstanding Paper Award, not once, but twice, for publications at AI Stats 2025 and 2026. And he also got the university's Outstanding Teaching Assistant Award. So despite his career track being very heavily research focused, then full-time software engineering, he's actually a very prolific open source builder. In fact, I took a look through some of his repos and I noticed that he has very comprehensive documentation for his own ML libraries, which is definitely a lot better than some of the stuff that I've made, which is supposedly production grade. And then when he's not researching or coding, he's also actually very interested in creating 3D prints and designs. He has a portfolio of custom models, such as like a 9-drive NAS, heat sinks, and even 3D vertebrae models. It's a lot more patience than I have in a hobby. See, today, Ayoub will be presenting his talk on hardware-aligned model compression, and he will specifically be discussing AdaSoft, an adaptive self-thresholding algorithm that spans unstructured and structured sparse training, one-shot pruning, and quantization, which notably outperforms baselines like sparse GPT. All right, so please join me in giving a warm welcome to Ayoub. And Ayoub, I think you can get started.
Okay. That's more detailed than I ever expected. Okay. All right. So today I'll be talking about using a famous algorithm, the soft thresholding algorithm, for inducing sparsity or pruning models. And there is an addition in our work, the adaptive part. We'll see how it works. And the goal here is not just to sparsify or prune a model, but to do it in a way that can be accelerated on the hardware level. This was mainly done with Stephen Becker. He's a professor at the Applied Math Department, and he worked extensively on proximal gradient descent and sparse coding methods. So he's an expert in the field, and his guidance in the proofs for the checking the proofs and everything was really helpful. So the theme of my research so far can be summarized as the efficient ML, or some people call it frugal machine learning. And when we talk about efficient machine learning, we are talking about 3 dimensions. The first one addresses data scarcity, and the common method to address that challenge is the unsupervised learning. So when we talk about data scarcity, it's usually the labels that are scarce. The second part is when the algorithms are expensive, are complex or expensive to run, then the solution will be to implement them more efficiently. You can think here about self-attention, and the smart implementation will be flash attention. And the third aspect is addressing the size of the models that are growing by the day, especially recently. And the idea would be to use more compact models or to distill into smaller ones. So that can be considered as a model compression. Okay. So my research combines these three. And initially, it was about data scarcity by leveraging representation learning as an unsupervised method. And the idea here is that if you are given a large set of data, you can think millions of nodes, millions of points, or even more, and you only have as information the similarity between the points. Okay, so that's the pairwise similarity. And the idea here is that how you learn a representation or a clustering that reflects that similarity. So in the application part, ultimately we use this for climate modeling, where you have massive amount of data from simulations, but we don't have labels. So we define the similarity basically at each different locations as the correlation between the dynamics of different variables. You can think like sea level, temperature, pressure, and other things. So once you define that similarity, we can create or find our clusters. And by doing this, you are not starting the neural network from a random initialization, but there's some prior knowledge. And by doing so in my research, we find that when we try to project these simulations to actual observations, the patterns will be different. So the top one will be the one that we pre-trained on probabilistic cut, and the bottom one would just be the one that was not pre-trained. And we noticed that by capturing these dynamics, there is some overlap between what the model learns and what the experts in climate science expect. But this method, these clustering methods and representation learning methods that I developed rely on using a backbone. You can think, for instance, about Dino V2, where you encode the images, you take the representations in an embedding space, and then you do the probabilistic cut or the clustering in the embedding space. But it turns out that these transformers and these vision encoders themselves are very expensive to run. So the question there is, how can we do that? How can we train or compress these neural networks in a way that we can stay in the efficient machine learning paradigm? Okay. So two ways that are commonly used for model compression: you have quantization and you have sparsity. Quantization is basically the industry standard at this level. The idea is that you reduce the number of bits that each parameter represents. The other dimension, which is the sparsity, it was quite popular for a certain period of time, but mostly the sparsity patterns that exist in most of the existing method algorithms target do not translate to actual hardware benefits. For instance, in convolutional neural networks, you have some sparsification methods that will randomly that will learn some sparse weight, but they are scattered in non-uniform way. And for instance, you can take just like a square 4096 matrix, and if you want to reach a sparsity level that will just keep the same performance, you need on GPU, you need to get like to 5% dense or less. So it's the relation between random or non-uniform sparsity and speedups does not translate that way. And the motivation behind leveraging this sparsity kind of started. It started before, back with optimal brain damage and optimal brain surgeon. But in 2019, there was the paper by Frank and Carbin about the lottery ticket hypothesis, especially for convolutional neural networks, that proved that you can take a very dense neural network like a ResNet 50, and you can cut up to like 90% of the weights, and you have negligible drop. But as I said here, the sparsity or the 90% sparse solutions that you find have this unstructured zeros patterns. So if you want to actually get a hardware benefit on GPU, it's probably 4 times or 5 times slower than just using the dense one. So it's fine for CPU or edge devices, but on GPU, that pattern does not help. And with rigging the lottery, which appeared 1 year later, the idea here is that you don't have to start from a pre-trained model. You can start from a randomly initialized model, but then you alternate between pruning and growing. So in pruning, you zero out the smallest magnitude, and in growing, which I call recruiting, you base it on the magnitude of the gradient. Sorry. Yeah. So for weights that are already in the support, you base your selection on the magnitude, so you remove those. But those that are already zeroed out, you rely on the gradient with respect, the loss with respect to those gradients to recruit more, and then you kind of anneal the sparsity to your target. Usually you start with 30%, and then gradually you go to 90%. But then, as I said here, in both of these cases, the performance does not translate to speed up, or the level of pruning does not translate to speed up. So the patterns that keep the performance do not give faster runtime, and the ones that actually fast do not necessarily translate to faster to better performance. There's also the other problem here, which is the annealing and the scheduling. It works for ResNet 50, but then if you change to ResNet 32, then you have to adapt that scheduling. So there's a lot of ad hoc and heuristic aspect for this kind of methods of pruning. So our goal here is to find a principled approach so that we can compress a model either during the training, train it in a way that is sparse, or after it's trained in a way that we give that memory and computation speed up. So first thing, I'm gonna give here an overview of specific case of hardware. So when we say hardware are aligned, what do we mean exactly? But this is very specific to NVIDIA GPUs up until Hopper, I think, and other devices or other platforms can have different things. So this is just a classical drawing from NVIDIA website about the logic of the GPU. Usually in the GPU memory, we have the model weights and the activations. So the first thing we do is that we copy these weights and activations to shared memory. Sometimes we go through the L2 cache to accelerate reuse. Once we have things in the L2 cache, we have the load and store instructions that will copy those ways to register file of the local threads. And once you have these weights in the register file, you would call the instructions that use the tensor core to call these atomic matrix multiplication instructions. So in this presentation, I'm going to use a very miniature example of a tensor core layout. We assume that the tensor core on the GPU just does 4x4 matrix multiplications. Okay, and for each and to issue this instruction, 8 threads have to participate. So we have the A fragment or the left fragment here, where we have 8 threads. So each hue of color will be assigned to one thread. So thread 0 will own A00 and A01. Thread 1, the next 2, and vice versa. For B, it's the same thing, but it's transposed. And then you have the result. Okay, so thread 0 will contribute A00, A01, B00, B10, and will receive C00, C01. Okay, and the idea here is that all threads have to participate, and they all have to contribute the same amount of elements in sync. So the tensor core rules, or at least for this model that I'm using, first thing is that all threads work in lockstep. It means that they have to issue the instruction at the same time in sync, and all of them have to participate. Okay. So for instance, I use this example here. If we take A and we decide that thread 0, all its elements are zeros, thread 3 will have all its elements zeros, and vice versa. If we want to issue this matrix multiplication, all threads have to participate, so all of them have to provide some elements. So in this case, thread 0 just have to provide 0, 0. Okay, you have to provide zeros everywhere. So here, matrix A is 50% sparse, but we don't get the 2 times speed up, okay, because all threads have to participate and they have to provide some elements. Okay, so this is a 50% sparsity, even though it has some structure, but it does not translate to like 2 times faster. So to describe what I call, or what we call, structured sparsity specification, I'm going to introduce basically the abbreviation of this, what I call S3. And the idea here is, yep. No question?
Sorry, that was me. I was making noise.
Okay. So with S3 specification, I use three levels. If you are familiar with Qt or Cutlass, you probably gonna get the intuition behind it. But the view is just the way you view the tensor in memory, or basically logically. The second level is what I call the block, and the third level is the scope. So the view is how you reshape the tensor. The block is the unit on which that we will prune, and the scope is, just as this name suggests, is the scope on which we decide which blocks to keep. Okay, I'm going to see how we can describe some of the famous patterns. So the first one is the 4 out of 8 K sparse. So this is supported by NVIDIA GPUs for 4-bit weights. So for this 4x8, the block has 2 elements, and the scope is 4 blocks. Okay, so in this case, the view will just be the 8x8 matrix. The layout will be row measure. The block will be 1x2. So those are just 2 contiguous row-wise elements. If we apply the block, then we get a block grid of 8x4. And the scope will be the 4 row-wise contiguous blocks. Okay, and then the 4x8 means that we're going to keep half of those. So when you apply K equals 2, then for each scope, we're going to remove 2 blocks. Make sense? So by defining the view, the block, and the scope, and the sparsity level, we manage now to describe what the 4 out of 8 K sparsity pattern is. For the 2 out of 4, then the block will be just the elements. It means that the block will be just one by one. Here I introduce a different pattern that I call 1 out of 2 M sparsity. So here we have 8x4 matrix that we reshape to be a 2x4x4 matrix. And we decide that we want to keep only 2 out of each paired rows. Okay. And once we do that, then we remove, let's say, the first row and the third row from the first tile, and the other rows from the second tile, and then we scatter them back to their position. So what you notice here is that thread 0 and thread 1, they end up with only 1 row, and vice versa. Okay, so there's only 1 red, 1 blue, 1 oranges, and 1 green. And the reason I choose this pattern is that we can start from a sparse matrix that follows this 1 out of 2 M, gather it to get a tile A, and then use the tensor core for 4x4 to get C. And once we do that, we scatter it. Okay, so in this case, we actually have, or basically built theoretically, a pattern that is 50% sparse and should get us around 2 times speed up, assuming that this gathering and scattering is cheap. That's the assumption. In practice, however, it's not really 2 times speed up. I implemented this in just CUDA and tried to saturate the tensor cores. For the A10G, I think Elkin will recognize this. This was used for the competition. You actually get near 2 times. But for the other GPUs, it's more about 1.5 to 1.7, especially for A100, because this scattering and gathering requires some tricks using the element-wise multiplications. And it turns out that A100, the tensor cores are way faster compared to the arithmetic units. Okay. Now we can also assume that the matrix A has 2x4 sparsity, which is supported by the hardware. And this is based on Cutlass kernel, even though usually NVIDIA market this as two times speed up, it's usually 1.8 to 1.9, even at very large shapes. Now we can compose both. So we have the 1/2 M sparsity composed by the 2/4 K sparsity. Just a disclaimer here, I call it 2/4, but in this case, it's just 1/2. I hope you get the idea. So now A, we do the scattering. We assume that the hardware supports that K sparsity, so you get 2 times speed up compared to the original. You get 2 times speed up from the K sparsity and 2 times speed up from the M sparsity, and then you scatter the results. When I compose the matrix, the sparse matrix multiplication with our 1/M, then we get around 3.4, 2.6 up to 3.4. So here it's a 75% sparse pattern that get us up to 3.4 speed up, which is not bad. Perfect. I'm missing a transition slide here, but the next step would be, okay, we have all these patterns, we managed to describe them. And the question here, how can we get or train a model or prune it in a way that will fit that sparsity pattern? And from the title, as you expect, we have the adaptive soft thresholding algorithm. So we will be using the L1 regularization. The famous regularizations, you have the L0, it is non-convex NP hard. I'll try to avoid that because we get basically no guarantees. We have the L1 sparse regularization, and we have the L2, which is the famous ridge regularization. L2 is preferable because the weights will try to snap to the axes, and that's exactly where the sparsity happens. All right. The other reason I use L2 is that we can define what we call the group L1, which is that instead of using the absolute value or the magnitude of the elements, you can define the groups. So in this case, the group will be the block. Okay. And if you use this organization and you train the neural network or some kind of model, you'll see that the sparse solutions will be pruning entire groups at once. These are also known as group lasso when we use quadratic objectives. Okay, I like using this example for why L1 organization actually introduces sparsity using mountain biking, because this is very popular here in Boulder. So the green here and the red are just two parameters that are trying to reach their optimum. We're starting with some weaker slope. They managed to go at least relatively a good distance, but then as we sharpen the slope, you see here that the parameters will try to or be pushed towards the origin. But with L2, the slope is never sharp, at least at the origin. It's very close to zero. So as long as the biker has some strength, which will be the gradient, it will never be sparse. Okay. On the other hand, for L1, the slope is constant everywhere. So once you reach a certain level, once the parameter basically once you make it steeper enough, the parameter will just be snapped to zero. Okay, there is no mercy from the L1 organization. But there's a counterintuitive property for the L1 organization, which is the non-monotone support paths, and this is valid even for very easy. Let's say the best case scenario objective. So here, this is just this is a quadratic function. It's strongly convex. It's convex, strongly convex. We know what the minimum is and everything, but we have the first component or the first parameter and the second one, they have some correlation between them. So what happens here is that if we start from regularization 0, which means we apply no soft thresholding, so here I'm just doing 3 elements, but you can imagine we have 4. As we are increasing the regularization at 20, at regularization 20, the green and the violet one will just will snap to 0. And as we are increasing, we expect that more will snap to 0, but on the other hand, the blue one comes back to life. Okay, and the reason here is that the blue one and the blue one has some correlation with the other elements, that you reach a point where the model will say, okay, instead of putting everything on the red, I will try to use both. So here I'll just plot the support as we are increasing the regularization. So at 20 here, we have only one active, but then we reach 30, the blue one comes back to life. So there are some papers, I don't want to name them here, but many of them will just say, okay, we're going to, if we want to sparsify using soft thresholding, start with a small value and increase it until you reach your target sparsity and stop. But here we have the nicest case possible, strongly convex function, and that does not hold. It means that as you are increasing the regularization, you might surpass your sparsity budget, and you can just oscillate. Okay, if you say, oh, I'm too far ahead, let me go back, well, there's no going back. So here, if you want to target 2, you are at 3 and then 1, you say, oops, I want to go back. Well, there's no 2 here. Okay, so the next slides basically would be about how can we tweak lambda in a way that we get the target sparsity. And these are 2 correlated parameters that are helping each other to get to their target. All right, so now we start the math. If you have some questions, just stop me, because later things will stack up. So the idea is that to train a neural network or to prune it in a way that we get the sparsity pattern we want, we're going to assume, in this case, everything is nice. We are just working with element-wise blocks. There's no groups yet, and we're going to use lambda and then try to find lambda that will give us our target sparsity. So the optimization pattern or the optimization algorithm for this objective is that you apply the gradient and then you apply what we call the proximal gradient. So this is just projecting in an L1 radius from the current update. All right, so you take the magnitude, you subtract the learning rate multiplied by lambda, and then you multiply by the sign, and that will be the proximal decision, the property. At the optimum, so if you assume that we converge to the optimal solution, this is the Kuhn, this is the KKT conditions, which says that at the optimal, we're going to have that minus the gradient is in the subgradient of the L1 norm. And the subgradient is just saying that if W is not 0, the subgradient will be the sign of W. And if W is less, and if W is 0, then the subgradient is anything between -1 and 1. Okay. The point I want to point here, that this condition does not tell us anything about whether Wi is 0 or not. The reason is that at these boundaries, at minus lambda and lambda, so if the gradient is equal to minus lambda and lambda, the W can be 0 or can be non-zero. So this is not, there's no sufficient or necessarily sufficient condition or property that this gives us. Okay, because at the boundary here, you can have 0 elements that have, you can imagine like the biker has enough strength to just stay in their position, not go up and go down. So they can be at 0, but still have that property where their biking strength is just equals to the slope. Okay, but at the same time, you can have someone who is way up the slope, who's frozen, and they just reach the level where they can no longer move up. So that in that case, the slope and their strength are equal. So the strength of the biker does not tell you whether they are at 0 or not. So one theorem that we prove, which gives us the intuition here, is that assume that we let the algorithm run and we reach the optimum. So the optimum is the W star. And I want to check whether a component is 0 or not based on the gradient. The only information I have is the gradient. So this theorem is saying component I is 0 if we have converged. So the biker I is 0 if you let the bikers bike to their respective positions as much as they can, and then take that biker and put him back to the origin of the slope. If their strength is less than lambda, then they will never move out of 0. Which is counterintuitive here, because you're saying, well, let the bikers move and reach their target positions. So we already know what the optimum is, and then put one of them to the origin and see if they have enough strength to move. So you say, well, I already know the optimum. I already know what the bikers will end up. So what happens here? And we're going to see how we can exploit this property. So the idea here is that if a biker is already in their optimum position, right, then the slope is pushing them downward, and the grade and their force is pushing them upwards. So the targets they want to reach and the resistance that they are subject to are opposite sign. Okay. And the intuition here is that, well, if they are outside 0, I'm just going to push them based on their position. Okay. So if they are at 0 and I want to change the gradient, they are already at 0. So if I add 0 to the gradient is not going to change. But if they are up the slope and I give them more strength based on their position, they can become more strong. Make sense? Okay. So here, if at the boundary where the gradient and the slope, or basically the gradient and lambda, are equal, if I add alpha W0, I can push the gradient slightly upward of lambda. Okay. So if the biker is at the starting point, this term adds nothing. But if they are not, then they're going to move up. All right. And this whole story here is the gradient minus alpha Wi, because as we said here, the gradient will try to, this force will try to push you up. So it will try to increase the position. So this score here is what we will be relying on to decide which ones to keep or not. Okay. And here the problem is not regularization problem, but we call inverse regularization problems. In the forward problem, what we do is pick a regularization and see what the solution you get. Here it's different. We want to pick a regularization based on the solution that we want. So in this case, lambda will be as a function of the sparsity level that we want. So the 0 norm is just the numbers of 0. The naive solution, as I said, is to just sweep all possible lambdas that you can. But in practice, if the model is too complex, that can be very expensive to do. And of course here, so far, I just kept the model simple, where we have those blocks that we want to keep, and we have one parameter per scope. So in this case, we have one scope. But imagine the scope are those rows of the matrix. So you're going to have lambda per row. And we're going to adjust lambda to only keep 2 elements per row. All right. And this is the second theorem that we have, which we call stable regularization. And it says that if you take any continuous positive function, there exists a lambda such that lambda is a stable point of this function phi. Okay. It's kind of counterintuitive. You're saying we'll take any continuous function, and if you take the optimal solution, apply this positive continuous function to it, you can reconstruct lambda back. So you can think about anything you want. Okay. And the reason here is that if lambda is too small, you can get any value, positive value of psi you want. But if lambda is too large, you're initially going to get to 0. Okay. So the phi curve is always going to start with something that is strictly positive and eventually goes to 0. It's as simple as that. So there is some lambda for which it's going to cross the first diagonal. The proof is basically 4 or 5 lines. Okay. Now we combine the two theorems that we have. Okay. So the first theorem says, well, Wi at the optimum is 0 if and only if we get this property. And for any continuous function phi, you get this property. So the question now is, how do we choose phi to get this inequality here? Any guesses? Okay. So the first inequality says, if at the optimum a biker is weaker than the slope, they're not going to move. And the second theorem says, for any slope, for any steepness, you're going to have a solution for any function, a positive function. You can find a steepness for which this function holds. Okay. So by combining them, so the trick here is that we just take these quantities for the different components and we order them, and we set lambda to be the kth largest value, as simple as that. So if we take all these components for these values for the different components, we choose lambda to be equal to the kth one. So this inequality is satisfied by the other non-k values, and we can guarantee that they are 0. Okay, so this is the function that we define. We take these values and we take the kappa plus 1, or kappa just the sparsity budget. So you see here that I removed the star. So it means that I don't need the solution to be optimal anymore. Okay, so I sort those values. I find the threshold. The ones I keep, those are the strong bikers. So those are going to move from the origins. And the other ones who have less strength at the origin, those are going to be improved. And we already proved in the theorem that we can find a steepness for which the equality holds. So it means that there is some steepness of the slopes that will keep me exactly kappa, kappa. So kappa plus 1, I think I made the error here. It should be kappa plus 1 equals 4. It's correct. So the ket will be 4, not 3. Okay. And lambda is simply the value for which this equality holds. So lambda is the root of phi minus lambda. So now all I have to do is to compute this value. The problem here is that it can be expensive to run. Why? Because I have to evaluate the gradient at w minus I. It means that if I want to evaluate these values, I have to take the bikers, maybe I have millions of them, let them bike to their destinations. Then each time, take one of them, put them at the starting point, and evaluate their strength. And you can imagine in a neural network, that's like, let's say, millions or billions of backward passes. So we can do things a little bit easier or cheaper by simply replacing that gradient at the origin by the gradient minus alpha w, which we kind of seen before. So it means here that you take the biker at their respective position, you don't move them, and you just give them a slight push upwards to evaluate their strength when they will move a little bit upwards. So the logic here is that as the bikers are biking upward the slope, the more they bike, the harder it gets. So you want to anticipate what their strength will be in the next step, and you want to put that slope, that steepness as the threshold. Okay, so if I know the biker is going to be, let's say, 20 Newton strong in the next step, but currently they are only 19. If I put lambda equal 20, they're going to be snapped or pushed back. That's the kind of the intuition behind it. And it turns out that this objective can help us recover many of the existing heuristics that we found in papers. So in the Regan lottery, if you remember, if the weight is 0, that is, it means that it's outside the support. We said we're going to recruit from the 0 elements based on their gradient magnitude. So in this case, this term disappears, right? But you can imagine alpha is very large. So for the ones that are already non-zero, the order of magnitude will be mostly based on the magnitude of the weights. So we prune those that have the smallest magnitude. So if you choose alpha very large, you basically get the Riggin-Delattre heuristic. But here, with a more principled approach, with all the proofs and all the math and niceties. If we choose alpha here to be the diagonal of the Hessian, we get something very similar to optimal brain damage and optimal brain surgeon. Of course, for optimal brain surgeon and optimal brain damage, we have more like the integral of this. So this is basically the instantaneous score or the instantaneous saliency compared to the optimal brain damage and optimal brain surgeon. So by changing or by choosing your alpha in a certain way, you basically recover all these algorithms that we mentioned, including these, I think, optimal brain damage from 89 by Jan LeCun, and Resurgent, I think 93 by Hasibi and Becker. Okay, so now we define what we call the adaptive software thresholding algorithm. We put everything together. The idea here is that we just use gradient descent, apply the proximal gradient, and then update the lambda to track that kth plus 1 statistics based on the gradient. Okay, so the gradient will give us how strong the bikers are, and we want to track the kth plus 1 strength so that we only keep the top k from all those from all those parameters. And as you see here, we have this adaptive approach. I think I made the mistake here. The alpha here is not the same one from the score. This is, you can look at it as the exponential moving average that we track, and eta t is the learning rate. So we proved that there should be some relationship between alpha and eta t, at least for the deterministic case. For the stochastic case, it's the same thing. It means we need to adjust the steepness of the slope slower than the bikers move, because if we are too fast, we'll just push them, all of them, to the starting point. So the theory just says that the speed at which we adapt the steepness should be slower than the speed at which the bikers move. So theoretically, we proved that we get all the convergence guarantees. 1 over square root of t is not good in the deterministic case, but we are interested in the stochastic case. So it doesn't hurt for the stochastic case, because that's what we'll be interested in for the neural networks. We proved that everything converges, the parameters converge to a stationary point, and lambda t will also converge to a finite limit lambda star, and the realized density will converge to the target density. One thing I did not mention so far, but I should be transparent on, is we can only guarantee that at most k parameters will be non-zero, at most. Because imagine in that slope, you can have some bikers who have the same strength profile, and they just sit on that boundary decision. Okay, so you can only prune them together or keep them together. So this is something that we have to keep in mind. Of course, we can make some assumptions to move that, but it's just going to be theoretical. There's no guarantees. All right. Here we, as I said before, how we can show that this adaptive software thresholding algorithm can recover the other approaches for either Riggin-Delattre, OBD, OBS, or WANDA, which is basically sparsity GPT without the compensation. Perfect. Yep. So this is just repeating the same idea that I've mentioned. If you choose your saliency score differently, you can recover many of these approaches. But the interesting thing is that we don't have to, for example, Riggin-Delattre, we will use a cosine schedule. We don't have to do that. And we also don't have to snap the bikers based on their current position. We can then let them move around to see how they adapt to the movement of the slope, which Sparse GPT and other methods, they don't do, because they just do one-shot pruning. Okay. So this is a kind of a classic example based on some classic benchmarks from sparse coding, as used in some papers by my collaborator Stephen Becker. And here I just show that if I do a lasso, which means that I just sweep lambda to see where if I reach my target sparsity, or if I just run my algorithm and I let it run until I reach my target sparsity, I get the same curves. Okay, except that with the sweep, I have to run the algorithm for all the possible values of lambda. And in this case, in our algorithm, we don't have to. Just let the algorithm run. It will adapt it automatically. And we see that it mostly overlaps. It actually even does better slightly on the upper, on around 0.3. That's like the L1 norm, the delta or the relative norm. Okay, so I will now move to LLM pruning, where I will compare to sparse GPT. So with sparse GPT, what it does is that you capture some calibration batch for each layer. So the entire stack in the neural network, you only look at one linear layer at a time, and you treat it just a linear transformation. You get that out, you get that input, and the idea is, how can I prune that layer so that the output stays as constant or as close to the original as possible? And this problem itself, as I stated now, is NP hard. And even in some other heuristics, we can do some other heuristics that are very complex, because what happens here is that each time you make a decision of pruning elements from a column, you have to adjust the other ones to compensate for the output that you have lost. Okay, and now you have, let's say, thousands of rows, and you have to do that at each row. Things get complex too fast. So for sparse GPT, what it does is they're saying, well, we'll use the same kind of logic of the optimal brain surgeon, but we'll do it column-wise, from the left to the right, which means that you can share the same Haitian at each level between all the rows. Okay, and you do this gradually. In our case, we don't do that. We just take that linear layer, we compute the gradient at each time, and just follow the gradient. We don't have to do any Haitian. We don't have to do any inverse. Just follow the gradient, and it will lead you to the results. So I run this on the Coin 3 family from 1.7 to 14, and on the perplexity score, which is the common one but not my preferred one, the adaptive soft thresholding algorithm is consistently better, especially the smaller the model is. The smaller the model, the more resistant it is to pruning. And in this case, I use the 2 out of 4 sparsity, and I measure the speed up for all these projection layers on my local 390. So at the end, you get like 1.70 to 1.9, depending on the sequence length. So in this case, we are looking at the prefill. Speed up for the decoding, it's just going to be around 2 if we reduce if we ignore the launch overhead of the 2.4 kernel. There's, for some reason, 2.4 just it has some more overhead than the dense one at small shapes. I don't know why. Here we have some usual benchmarks, mostly the pre-training one, except the MMLU, and Astra for the 1.7 is better. The main observation is that the adaptive soft thresholding, when we are doing zero shot or one shot pruning, similar way as sparse GPT for a fair comparison, is consistently better than sparse GPT at smaller models. As we move a little bit a notch for 4B, they become competitive on MMLU, or let's say on post-training metrics. And at 8B, sparse GPT also catch up on the ARC challenge. And on the 14B, I'd say they are mostly not that different, except some noise, except on ARC Easy and ARC Challenge. I would consider these as relying more on memorization. So the pruning will hurt most the benchmarks that rely on memorization, less than reasoning. And also, the larger the model, the two methods kind of get very close to each other. Perfect. Yeah. So here, mostly the knowledge-based benchmark will degrade based on pruning, and for the reasoning is mostly preserved. Kind of Winograd kind of improves after pruning, and also Lambada, which is kind of weird, but it's within noise. Okay, so you don't lose any on those benchmarks when we use Astra. So to summarize everything so far, we have introduced a sparsity specification framework where you describe your sparsity pattern, and then you plug in our adaptive soft thresholding that will adjust lambda for each scope. Okay, so for 2 out of 4, we have 4 weights. We want to keep 2. We have 4, let's say, bikers. We want to keep 2. So we adjust the slope strength for each 4 until we only keep 2. So you specify the S3, and you let Astra run, and it will take care of the rest. The sparsity patterns that we had described by S3, they can get from 1.6 to 3.5, but the sparsity pattern that combines the 2 out of 4K and the 1 out of 2M, that's just to show that we can get hardware friendly. We can describe new patterns using S3, but we never prune a model using that pattern, at least not yet. I did not include the sparse version of the adaptive soft thresholding algorithms, but just to give you a heads up about it, when we want to compute the kth, we want to compute the statistic, we have to keep track of an unbiased estimate of the gradient, because you remember we compute the kth largest value, so we have to keep those large values that we compute, or the saliencies, as unbiased as possible. So it means that we need a copy of the parameters. So that's the additional cost, is that we have to keep a copy of the parameters that track the gradients. I did not include the training time or training instead of pruning. But we can also use Astra either with a stochastic gradient descent or Adam optimizer. We already shown that S3 is very powerful for describing patterns on NVIDIA GPUs, but I can already think about other patterns like on the Apple Neural Engine, where the matrices or the atoms are 8 by 8. So you can think of pruning 8 by 8 blocks all at once to give those hardware speedups. Astra performs sparsity mostly up until 7 out of 9 benchmarks, and it can also use for quantization. And why? Because GPTQ and SparseGPT are based on the same approach, or the same core algorithm, which is the sequential optimal range surgeon. And already started using this for the competition me and Olgin were in, and it works pretty well. If you want to see all these implementations, I have the sparsity pattern already implemented and documented as a sparse kit. And for the quantization, I have a toy package. For now, it's mostly just math and some slop code. I would not recommend to rely on it at this point. And the other packages can be found on my GitHub. So far, Astra is not documented and released, but you can find it on my GitHub as adapt soft for adaptive soft thresholding algorithms. I want to show you the sparse kit. I want to show you an example of how easy to use the sparse kit. If I can go just to quick start here, all you have to do is describe what the block is, what the scope is, which is 1 out of 4, and then you can run structured. Okay. So all you have to do is describe what the block, the size is. If you want to do out of 4, what the scope is, which is 4 elements, and then you can run something like structured OBS. Structured OBS is just a a more faithful variant than SparseGPT to the optimal brain surgeon variant, but it's way slower because we don't do the sequential column. We have to go basically one row by row. For magnitude pruning, which is just the hard thresholding, things are way easier, right? You just, hey, I wanted to keep 2 non-zeros, and you threshold everything. Yeah, I think it's well documented, at least. I went through it one by line. And then you have also the builder API, which is just an abstraction where you can define the blocks, and then the scopes. The coupling, I did not cover it, but the coupling saying, if I have weights across layers and I want to make the decision based on these weights across layers. So what I do is, the logic is I just kind of concatenate them to create some virtual tensor. And so the decision can be done across tensors from different layers. But so far, I never used this because I haven't seen any application for it on the hardware level. Okay. All right, I think I'm done here so far. I try to cover quantization, but I leave it outside the presentation. But if you go to quantize package, if you go to the quantized package and you go to the optimal search and the Haitian aware, you can find all the math behind it. The idea behind the quantization is that instead of targeting 0, we are going to target the quantized version of the weights. That's the whole idea. But the question is, what is the optimal quantized version of the weights? And I covered that in the write-up in the package. With this, I end my presentation. So if you have any questions, let me know.
So I had one question.
Yes.
So when you do this kind of structured sparsity, if it allows you to basically take advantage of hardware in a way where you are getting speedups in the training that you do, because you're just using less cores.
Yep.
Does this also mean that you get memory reductions in the way that the algorithm works? Or is it still like a fixed memory that you have to load?
Good question. So it depends on the pattern, right? If the sparsity, if the pattern is random, you have to keep the index for each one block. But let's say 2 out of 4, as in NVIDIA, you only keep like 2-bit index for each element. So if you know the pattern is what the pattern, if you know the pattern that you are targeting, you can use bitwise, like just bit masks to do that. And the bits compared to the size of the bit size of the parameters is usually way smaller. The second part I think I have to mention is that this method is more about inference optimization, because during the training you have to keep track of all these gradients. So even though some of the weights can be masked during the training, the benefit is at the inference time where the model has converged to your sparsity pattern.
Yeah, I think that makes sense. So the reason I ask is I think there's a few methods, like if you have some kind of KL regularization and you have to load a reference policy, or maybe you want to do like weight decay, but you want to do it relative to the base model. So I think kind of similar to what you were describing, but instead of decaying to 0, they just decay back to their original base. Could this kind of pattern allow you to train and essentially store both for the cost of one?
You're just saying we are kind of having a different 0 or a reference instead of the 0, but I don't see how you could do that.
Like maybe if you're going to be zeroing things out.
Yeah.
I don't know, because I haven't worked in depth this much with hardware, but like maybe I don't know if there's architectures that when you zero this stuff out, it allows you to actually save storage somewhere else, like memory somewhere else. So
Okay. that's the main idea, is that we're not only interested in fast computation, we're also interested in less memory. So if we use the 2 out of 4, you get like that 50% model reduction. I started playing with the JAMA 4 model, the 31 billion, and I noticed that the first half of the layers, you can prune the MLP layers to 2 out of 4 without losing anything. You see more once you move through to the second half. The pruning starts to become stronger. So let's say if you take HEMA4 and you just prune the MLP, which is most of the neural network for the first half, you can reduce up to like 25% of the model before even applying quantization. So if you add quantization, you can even add more benefit. But the idea here is that, yeah, you have to target a pattern that you can encode cheaply without adding more memory.
Yeah, makes sense.
Yes.
Yeah, I have another question.
Yes.
Yeah, very nice work, and thanks for the presentation. So I wonder, maybe I was missing something, but I think you didn't talk too much about the objective function, the asking function. But I wonder, for the language model, did you kind of like share GPT paper, you take each block, minimize the L2 difference between, like kind of minimize the L2 difference before and after the compression, or you choose a loss function that's kind of end-to-end loss function, right? The KL.
So for this case, I wanted to be fair to Sparse GPT, so I use their same objective. Use the same objective, even though our method is more general. And actually tried to publish this, but some reviewers pushed back saying, well, it's not a fair comparison. So let me show you, for instance, something here. So on the 1.7 model, the Qwen 1.7 model, what I did is I went ahead and then let me share this one here. Okay. All right. So in this case, I have followed my gradient approach for this case. So the 1.7, I used a pretty large number of samples. I use Sparse GPT to prune the model, and I use Astra to do the same thing. And the reason Astra becomes stable is that at each layer, as we are pruning each layer, our goal is to target the original model outputs, okay? Which is different from Sparse GPT, as it propagates the outputs. It means that if I prune the first layer, it means that the outputs are going to be different. But for the second layer, I don't try to reconstruct. I try to recover the original model. So I am pruning and I'm recovering the original outputs instead of doing like Sparse GPT, where I just propagate at each layer. So when we do that, then we do even better compared to Sparse GPT. I mean, Perplexity 1000, which the model just was destroyed. It's not useful for anything at this point. But for the benchmarks I showed you, we do the same thing as Sparse GPT. We keep just take the input at each layer, propagate, prune, and vice versa. So we're only looking at one layer at a time. If we use the gradients, we get even more powerful results. But it means that you have basically to do a full fine-tuning of the model, which can be expensive.
Okay, got it. Okay, thanks.
Yep.
I have just maybe one other question. So there is this one quantization paper. I forget the name of it, but basically I think they went with an idea of they want to progressively quantize a model, and they want to have like a shared code book. And I think they do like the quantization first, and then they in the next layer I think they do error correction, and they just keep alternating the subjective. I don't know if that's something you're familiar with, or if that's something you tried.
Can you say that again?
So they first do a round of quantization. So I think they train with respect to quantized objective. And
Yes.
then the next round they train for an objective of error correction. So they take an unquantized layer, and then they correct it for the error that would occur in the layer before it.
I see. It's kind of the same logic, except here I'm agnostic to the quantization. So instead of 0, you can put your quantized version as the 0, right? And instead of snapping to 0, you snap to the quantization aspect. The only problem there is that I see, for instance, people using a straight-through estimator, where you just fake the quantization and try to fine-tune the model. Theoretically, it has no convergence guarantees. If you train the model, you can just keep oscillating. But with the thresholding, you're actually forcing the weight to snap to the quantized version. But yeah, so imagine here, like the bikers have to go to quantized positions. So here you're saying, I'm going to quantize the weaker biker and let the other ones go with whatever they want, and then compute the new quantized version and reiterate, right? Until everyone is quantized. So you allow compensation to recover the loss that you have.
I see.
Yep.
All right. Does anybody else have questions? All right. If there are no other questions, let's all thank you for giving us this awesome presentation.
Thank you. Yeah, if you have any questions, just send me an email or put some issue on the repositories, and I'll be happy to answer.
All right, thank you.
All right.
Have a good day.
Thank you.
See you.
Bye.